Today we begin our study of integration, which is the opposite process of differentiation. Now we begin with a concept of the definite integral. Now integrating is all about finding the area underneath curves. So in this case, we have some function here, y equals f of x. And we're finding the area here that's underneath the curve, bounded by the curve and the x-axis. And it's called the definite integral because we're actually giving it some boundaries on the left and the right and saying we have a definite section here that we want to find. We'll also later look at how to find the indefinite integral, which is what happens when we're not sure where these two parts might be and we come up with a formula that's nice and general. So let's just take ourselves back a step. A lot of the area formulas that we've already learned, the area of a triangle, the area of a parallelogram, a trapezium, are really based on the area of a rectangle, because if we make a few choice cuts in those shapes, we can come up with those other area formulas. And we're going to do the same thing here, even though we're working with a curve. Now, to make a rectangle here, we're going to go ahead and cut up our space. Let's just take a random point that might be inside the area that we're looking at and call it x. Now, we're not sure exactly what function this is. It could be part of a parabola or an exponential curve. We're not sure. But whatever it is, y equals f of x, it's some function of x. So if we were to say, all right, what y value does that x line up with? We'd say, well, this is a function of x. So if you plug in x, what you'll get as the y value will be f of x. Does that make sense? So let's go ahead and draw a rectangle. We'll make it sit just to the right of our x. Now you might be wondering, how wide is our rectangle going to be? Well, we're going to make it really small. So I'm going to call this width here a small change in x. So this is the symbol delta, which means a change in x. So x has got a little bit bigger moving across here to the right. I now have the width of this rectangle. So you might ask, well, how tall is it? Well, the rectangle is still f of x tall. And you'll notice that the wider it is, the more it's going to look awkwardly like it's sitting below my curve. So it's not going to approximate the total area very well, is it? But if I make this change in x really, really, really tiny, in other words, if I keep on building more and more of these rectangles and they're very, 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 very skinny, then if I can work out the area of each rectangle and then add them all together, I'll have a very good approximation for the area of this whole space under the curve. Now, think about the area of a rectangle. It's base times height. The base of our rectangle is just a tiny, tiny change in x. And what's the height of our rectangle? Well, for this one here, it is f of x. So we write it like this. But we know, of course, in algebra, we can leave our times signs out. And I'm also, for the purposes of our notation, going to switch these around and basically call it area of a rectangle is height times base and write it like this. And I don't need a times sign between the two because we're using algebra here, so we're going to smush them together. And this now forms the basis for our formula for finding the area of this entire space. So we've written here, to find the area, we can add up the area of all of the rectangles. Now, we've seen this symbol before. This means sum. It means add everything up. And we've seen this when we were looking at data. It says add up everything from when x is A all the way up to when x is B. We're going to add all the rectangles together. Now here we have the formula for how to find the area of any one of the rectangles. It'll be f of x times our small change in x. Now here with our notation, we've cleverly changed delta x, or a small change in x, to dx. And you saw that same notation when we were looking at differentiation. There's something else out the front here, though, that we haven't considered. We're taking the limit as the change in x approaches 0. What does that mean? Well, we're saying we want to add up the areas of lots and lots of rectangles, but we want the rectangles to be as skinny as possible, because if they're really, really super skinny, we'll have a very good approximation for the total area underneath the curve. So we're taking a limit. Now, this is a nice formula and it describes really well how we're going to make the rectangles skinny We're going to add them all up, and this is the formula for how to find the area of each rectangle. But to simplify things, we can take this whole part and rewrite it like this. And this symbol here looks a little bit like an S that's been sort of stretched and stylized out. It means take the sum. And we use this symbol when we're integrating because it basically tidies up our notation. Now you'll notice it still has the A and the B on it. So this symbol means take the sum from when x is A all the way up to when x is B. And if you're thinking, well, what are we taking the sum of? We're taking the sum of this, f of x dx. Now, this gives us then an actual definition for what this formula means. This formula is defined as the area bounded by y equals f of x, the x-axis, A, and B, where A and B, as you can see, are these vertical lines, where x equals A and x equals B meets the function itself. Now, there's another new word I can introduce you to. F of x, or whatever is written in here, is called the integrand, because that's the part that's going to be integrated.